Alright, let's restart this session by before talking about showing that the image of the compact set under continuous function is a compact set, showing that the image under continuous function of a connected space is a connected set. I'd like to show you an important, quite immediate consequence of the new concept we have constructed, that is the notion of continuity by means of open set or closed set. You will see that here it's the proof is quite elegant and fast. Assume you have to have two functions, g and f. G is defined from E1 and takes its range in E2, and f it takes its sources in E2 and takes its range in E3. Those three spaces are occupied with different metrics. I do not need to know them. I claim that I assume that those functions are continuous everywhere, f and g. Well, I claim that the composition of f and g is also continuous. Let's go back to the things we did in the real case, and this is something that you guys have seen in modern analysis. If those three spaces are, let's say, subspace of R, intervals in R, we knew that how to do this, but it took time. It really took time to show that the composition is continuous, and you really have to deal with the metrics. So if those 2 points are close enough to one another, then the image are close enough, and then because their image are close enough, arbitrarily close, then the composition with the next function will be eventually as close as we want. So that's pretty much the idea here. But we don't have to do that in this case. We just have to take an open set here, take the preimage by f. It's still an open set because f is continuous. To this open set, since it's an open, because f is continuous, f minus 1 of u3 is again an open set of e2. Take the preimage under g of that set, so g minus 1 of f minus 1 of u3. And it's an open set of E1 because G is continuous. End of the game. So G minus 1 of F minus 1, of course, you guys have understood that this is nothing else than G composed with F minus 1 of E3. Sorry. No. F composed with G minus 1, sorry. Obviously. I'm asking you also to show, actually this is pretty much paraphrasing what I have just said. Instead of taking an open set anywhere, just take a neighborhood at the image of the point. Let's say what I call it x0. Take f composed with g at x0, and I claim that if f is continuous at g of x0, g is continuous at x0, only, say, a priori only, then f composed with g is continuous at x0. You just have to rephrase open set by a neighborhood of, and it goes pretty much the same. You don't even have to touch the matrix. This is also the beauty of topology. Sometimes you don't have to touch much the metric. To complete this entire discussion that you see in the case, for example, where the goal here of function g is the space of real numbers occupied with the Euclidean space, for example, you want to show that if f is continuous, g is continuous, then the product is continuous, or the sum is continuous, or linear combination of f and g is continuous. Well, this is, I'm saying this is pretty much redoing pretty much the same thing as we did in the real line. And on the top of it, what we end up showing is what we could show, showing that a function is continuous at a point. It's sufficient to take a sequence of points tending to the point and looking at the sequence of the image. Since the sequence of the image will be a sequence of real points, then I can refer to everything we know from modern analysis and the things we have seen in the former videos. I think it was in matrix space 2, if my memory is correct. and you can redo exactly the same thing, paraphrasing everything, and you end up with what we have in chapter 3. So please read chapter 3. Paragraph 3 in chapter 4. But I hope you understand this will be pretty much redoing the same thing we have done in the context of real numbers, in the context where the map takes their range in a real set. Alright, so now let's move on and go back to the two theorems I stated last time, and now I'm going to prove it. So I'm going to start first by proving that a set which is compact is mapped under a continuous map to a continuous set, compact set, sorry. So more precisely, let me rephrase this this theorem in a better way. Clean the ball first because it's okay, so theorem. Assume that we have a map F defined from a metric space E D onto a space F or E prime with D prime, say. Okay, fine. Assume that F is continuous. E is compact, that's important. Then the conclusion is that F of E is compact. Alright, so one remark before I give a proof of this theorem. It is also true, obviously true, if you replace a map defined in a full space, if it's only defined on a subspace of E, but then what you have to look at is you want to make sure that this subset, let's call it K, is compact for the topology of E. And the image of K will be also compact because I can see simply K as a subspace of E. So since K inherits the distance from E, I mean saying that it's compact. Looking at a compact space or a compact set amounts to doing the same thing. That's what I'm saying. So actually, I want to give two proofs of this theorem. And you should not ignore any of those. Remember, in the frame of metric space, compacity and sequential compacity means the same thing. Well, this is pretty much what I'm going to show. E is compact or sequentially compact, you name it, same. I'm going to show that both are true. F of E is compact and is sequentially compact. More precisely, I will make a proof in each case in such a way that in the first case I would take covering, and on the other case I will consider subsequence. More precisely, let's take proof number 1. You want to show that F of E is compact. Okay, so let's take a covering of F of E. Let OI. So, okay, let's do it like this. Let OI, I belonging to J, a collection of open sets such that a collection of open sets of E such that of E prime such that the union of OI covers F of E. Alright. What do I do with this covering? You remember, I need to deduce a finite subcovering, and I do not know this. The only thing I know is E is compact. What I can do is definitively take the preimage of all those sets. So let's take the preimage of this union of sets. Well, the good news is that if I take a union of sets, the preimage of union is the union of preimage. If it was the direct image, I would definitively have trouble. But in the case of a union, I'm quite safe. So this is equal to the union from I belonging to J of f minus 1 of OI. And because this set was covering f of E, this definitely covers f minus 1 of f of E. Which definitively covers E itself. I mean, f minus 1 of f of E always contains E, for sure. That's also, these are classical probably from, let's say, set theory. So, I mean, I want to refer to the knowledge you learned, for example, in discrete math or in modern analysis simply. All right, so, well, this means what? Okay, so this is open. Those guys are open because F is continuous. The preimage of open sets are open. Oh, but okay, now E is compact, so I can deduce a finite covering for E. So let I1, IP belonging to J such that the union from J equal, no, not J, that's dangerous, K equal 1 up to P of U of f minus 1 of OIK still covers And now what I'm going to do, I'm going to map everybody by f. So let me erase now this part of the board. I don't need this anymore. Alright, so I claim that if this is true, what do we have? We do have, so here we do have f of e is included in so it's included in k equal 1 to p of f of f. So more, let's do it slowly. I want to say f of the union for k equal 1 to p of f minus 1 of OIK. Right. Now, I said that the union at set doesn't behave very well by means of direct image. That's not true. With direct image, the union works very well. This is the intersection which doesn't work very well. But with the union, we are good. So let me rewrite this correctly because it's not nicely written. So this was, as I said, the image f of the union from k equal 1 to p of f minus 1 of OIK. That's better. Okay, so, well, this guy is exactly the same as the union from k equal 1 to p of f minus 1 of OIK. So take the bracket as we need, and that's it. So in other words, the union and the f commutes. This is something that you can verify as the union of a function of sets. Well, this is equal to the f of the union of sets. This is easy to verify, just by simply by it's a set theory. Let's It's a classical set theory approach. Okay, so the temptation will be to say that f composed with f minus 1 of OIK is equal to OIK. No, it's not. No, it's not. But the good news is that it's a set which is contained in. So let me go one line further. So this is something that. So let me summarize the thing I've used about f. So I said that f minus 1 of f of a set A, say, this is always included in A. This is something that you can always verify. If you reverse the order, you have f composed with f minus 1 of a set B is always included in B this time. So let me say, for those which know those equalities, well, you can use it. For those who do not know, please, I leave it as an exercise. So it's just pure, it has nothing to do with topology, it's just purely set theory. All right, so that guy here, therefore, what we have here, we have that the union from k equal 1 to p of f minus 1 of OIK contains f of e. That's the one I want to know. But they are also included themselves in the union from k equal 1 to p of OIK according to this property here. Well, okay, you see, remember we started in the first place with a covering of OI where I belonging to J, and we finally ended up, which was covering f of E, we finally ended up with a finite subcovering of those covering. So this means that f of E is compact. F of E is compact. All right. And of course, f of E is also sequentially compact. But I'm going to give you another proof, proof number 2, which is going to prove that fact directly without using covering, but using subsequences. So now I can erase everything. Proof number 2, and I also advise you to remember this proof, at least to practice how to redo this proof yourself carefully, because this is a very standard thing that we ask in test or in qualifying exam and whatnot. I mean, we cannot imagine a student starting any a PhD program without knowing those theorem on the tip of their finger, honestly. All right, so. All right. So, proof number 2. Okay, so we want to show f of E is sequentially compact. Yeah, so one remark. I don't think that in qualifying exam or in a test, if I ask you to prove one theorem, you need to provide 2 proofs. Only one will be enough. But I strongly advise you to do both anyway. All right, so we need to show that it's sequentially compact. How do we start? Well, let's take a sequence. Let's Yn be a sequence in f of E. Well, if it is a sequence in f of E, that means that it is a sequence in the image of E. So this means that there must, for all n belonging to the integer n, there exists an xn belonging to E, such that f of xn equal yn. Yeah, because they are in f of E. I'm not saying that those xn are unique. No. There may be a lot, thousands of them for each of those n. But one is enough, and I take it, and I take a sequence. But now, xn is a sequence in E. Xn admits a convergent subsequence. So xnk as a convergent subsequence. convergent subsequence. So let's say x and k tends to x infinity belong to E. Right. I don't think that I will need x infinity. I don't know. And now f is continuous. What does f is continuous? So let's see what it takes now for yn. So I need to erase some place. So we had yn now. Let's take f of x and k. Well, this is nothing else than y and k. But x and k converge to x infinity, and therefore y and k would converge to f of x infinity, because what? Because f is continuous. So f is continuous tells you that the limit of the image of the limit is the limit of the image. That's the definition we have deduced before. So conclusion, I started with a sequence yn in the first place. I deduce a subsequence y and k, where y and k converge to what? To f of x infinity being a point in E. So this shows that any sequence in f of E admits a convergent subsequence, ending the proof of the theorem. And of course, f of x E belongs to f of E. That's quite clear. All right. So that's the two proofs that you need to know. It looks like actually the sequentially compact version is slightly easier than the one of covering. The one of covering is not harder. It's just that you need to remember a bit of those set theory thing, but it's not so hard. Actually, the good news is that maybe this one thing you have to remember. Those set theory properties are let's say in favor of what you are intending to say, which is a good news. But I would agree that the method using sequentially compact approach might be easier. Yes. All right. So now next theorem, which I want to show, and which I stated, it's about a connected set. So theorem. F goes from ED to E prime D, so it's pretty much the same setting as above. F is continuous, E is connected, then F of E is connected. All right, so now this time, I'm going to really using the fact that a space is connected. It's the unique set which are closed and open at the same time is the set E itself and the empty set. So I want to remind everybody. So E is connected, or E is a connected space. It's maybe better. If and only if the, let's say, infinity and E are the two open and closed subset of E. Well, remember what we did. We did before that I was talking about a connected set, not a connected space necessarily. By using covering of open, so I was saying that set K was included in E was connected if K can be covered by two open set U1 union U2 such that U1 union U2, so you got U1 union U1 intersected with U2 intersected with K is the empty set. This is the sort of thing I want to do. Right. Now, if you replace K by E straight, what does it mean that E is covered by two open sets? Well, I mean, E is covered by two open sets. There's nothing bigger than E, so it has to be equal. And of course, if you take you have to look at the intersection of O1 and U2. Of course, you cannot take all sets other than in E, because both O1 and O2 are in E these times. This is maximum. In this case, O1 and O2 cannot be bigger than E by means of inclusion. So this is what you got. So O1 is an open, O2 is an open, but since O1 is a complementary of O2, they don't intersect, you see? So if a point X is in E, is either in O1 or in O2. So that means that O2 is a complementary of O1, and O1 is a complementary of O2. But that means that both set O1 and O2 are closed and open at the same time. Well, the conclusion, it tells you that it is one of those is empty and the other one is the full set. That's what it says. All right. So this is this definition I'm going to use, the definition of a connected space. Not necessarily I'm using the notion of connected set. It's actually more it's more comfortable, to use the notion of connected set when you have to consider several sets in the space, in the corresponding space. Otherwise, if you don't consider the definition I gave before with the covering with open set or with closed set, remember this was a part of one of the exercises I assigned you. If you don't do this, you have to consider each set as a subspace itself. You have to change the topology at each time. That is not so handy. All right, but here in this case, I have only one set to consider. I don't need to worry. All right, so I want to show that f of E is connected. So let f of E equal the union of two open sets, U1 and U2, such that union intersected with U2 intersected with f of E. Yeah, well, okay, so I see that. Well, okay, yeah, here I need to consider again the general definition of connected set, because f of E does not necessarily coincide with E prime. So okay, let's f of E be covered by two open sets, U1 union U2. U1 open in E prime, U2 open in E prime, and I want U1 and U2 not to intersect themselves in f of E. Well, that's my setting. All right, so what does it take? I need to erase maybe the top. I'm actually up to here. We know what we are talking about. U2 open in U prime, in E prime. All right. So well, you know what? Let's take the preimage of everything. So the preimage of f of E. Well, this is going to give me E anyway. That's for sure. So f minus 1 of f of E. Well, here in this case, this C is equal to E. It actually, you can say it contains E. Well, I mean, it contains E. I mean, it can't be bigger than E, of course. And is included in f minus 1 of U1 union f minus 1 of U2. What does it mean, this? Remember, this is a good thing. When you take the preimage of the intersection of sets, the preimage of intersection is the intersection of the preimage. That's the good news. That is not the case when you take the direct image. But then I claim that f minus 1 of U1 intersected with U2 intersected with f of E is of course the empty set. The preimage of the empty set is the empty set. And then so this has to be equal to f minus 1 of U1 intersected with f minus 1 of U2 intersected with E. Well, E is equal to the empty set. So here we don't need to intersect with E because we know that everything is included in E. So this is pretty much obsolete here. All right, so what do we have? We have E is included in, well, again, E is not included, E is exactly equal to F minus 1 of U1 union F minus 1 of U2, and F minus 1 of U1 intersected with F minus 1 of U2 is empty. Well, this is an open set. This is an open set which covers E completely. Both sets do not intersect. So this one is closed, this one is open, this one is closed, and this one is open. Both are closed and open, they don't intersect. Well, I'm sorry, one of them has to be the empty set. One of them has to be the empty set. So let's say F minus 1 of U1 is empty. But if F minus 1 of U1 is empty, that means that F of E is completely included in U2. And that means that, yeah, that's right. So that means that U1 intersected with F of E was equal to the empty set. And this ends the proof that actually F of E must be connected because one of those open set has no trace in the set. That's what that was the definition of a connected set was. So I repeat maybe connected set. So U1 union U2 needs to cover F of E. That's what we were saying. And U1 intersected with U2 intersected with F of E is equal to the empty set. So if F of E is connected, what we should conclude, and this is what we did, either U1 intersected with F of E is empty, or U2 intersected with F of E is empty. And okay, well, we have chosen this one because it doesn't matter which one you choose, it could have been U2 if you want to. But that means that U2 contains the entire image of F of E. Alright, so this shows that F of E is a connected set. Alright. Alright, so now we have actually set up a quite solid base for talking about an important aspect in analysis about functions. So we have introduced the notion of continuous function, which is good. And now we're going to increase the quality of those functions. We're going to speak about uniformly continuous function. And you will see that the notion of compacity will also play a central role here. Just give me some time to clean the board. All right. So I need probably to remind you what does it mean for a function to be continuous. And then I will introduce the notion of uniform continuous. So great, recall. I don't think it hurts anyone by doing so. Let's say we have a function f defined from a space E with a matrix D to a space a Y with a matrix D prime, and we say that f is continuous at a point x if and only if. So I should say f is continuous everywhere that's bad. F is continuous if and only if for any x belonging to E, for any epsilon positive, there exists a delta positive, such that if y belongs to the ball centered at x and you have reduced delta, then f of y belongs to the ball centered at f of x and of reduced epsilon. Well, remember, this is the definition I gave, pretty much word by word. Now, that's the definition of continuity. Now, definition. Under the same setting. That is, f is defined like this. F is said to be uniformly continuous. And I will use this following shortcut, UC0. I'm not saying it's universal, but this is the one I like because it's a few words. If the following things hold. It's pretty much the same sentence except that we're going to interchange x here. So for it's not going to be by for epsilon or all epsilon positive, there exists a delta positive such that for all x belonging to E, if y belonging to if y belongs to the ball centered at x and of reduced delta, then f of y will belong to the ball centered at f of x and of reduced epsilon. Now you may say, oh, hold on. What is the difference between this sentence and this sentence? I've written pretty much the same thing. Actually, I've said exactly the same words. Same words. Well, yes, I've said the same word, but not in the same order. Here, you see here. It says for all x in E. Okay, fine. For all epsilon positive. Great, I understand. So I have the right to choose x and E, x in E and epsilon positive wherever I want, fine. But this sentence tells me there exists, for this choice, there exists a delta. Oh, but this means that the delta I've chosen here may depend on the point. It will depend on the choice of epsilon, but it also depends on the choice of x. Although here in this sentence, you have to read from left to right, choose epsilon, it tells you, well, don't worry, Archie, there is a delta that depends only on epsilon, does not depend on x, because the x comes after. So that's why we say it's uniformly continuous, because you don't have, the delta can be chosen the same for any point you are taking. Requiring, of course, that the epsilon is given. That's pretty much the difference. Example of functions which are uniformly continuous and some which are not uniformly continuous. So I'm going to leave this as an exercise. Let's f from E d to E prime d. So you can take any example you want. It could be from R to R with the same metric. F is alpha Lipschitz. So that means, remember that for all pair of points, so there exists, no, so alpha is included. So for all x and y in E, the distance prime of f of x and fy of x is bounded by k times the distance between x and y. K times the distance between x and y. Well, I can help you quickly for this exercise if you want to show that it's uniformly continuous. Choose epsilon positive once if once epsilon is chosen positive, take delta equal epsilon divided by k, and you will see that the function will be uniformly continuous with this choice of delta.